is Asma Afifah binti Ahmad Shamsuddin, member number 1.
Good morning to our panels. I'm Rana Yensingyi. I'm from Section 3, Group 6, member number 2.
My name is Nanunis binti Arifin and I'm member number 3.
Assalamualaikum and very good morning. My name is Nur Alwani binti Samad and I am member number 4.
A very good morning to our panels. My name is Yap Sili. I'm from Section 3, Group 6, member number 5.
Our IDP project title is Wireless Magnetometer for Vehicle Count and Monitoring on Thingspeak Dashboard.
Group introductions. We are from Section 3, Group 6, and our supervisor is Professor Madya IR Dr. Sun Ching Fong. Next, introductions. Magnetometer is the instrument that we use to measure the strength and direction of magnetic fields. As there is a significant increase in the number of cars used among Malaysians, data collected from Magnetometer sensor project can be used to analyze the intensity of traffic flow in Malaysia. Traffic control can be customized according to the traffic density in each region to ensure a smooth traffic flow. Problem statement. First, many problems occur due to the high number of traffic density such as environment pollution, depleted natural resources, and also increase of commute time. Second, improvement of traffic system include maintaining the transportation infrastructure statistic and also tracking the density level of the traffic so that enhancement can be applied. Third is that manually counting the car to gather the statistic data is not efficient. Next is our objective. First, to develop transmitter and receiver by using magnetometer, sensor HMC 5883L and RF433 MHz transceiver. Second, to develop gateway to connect to the computer or mobile phone. Third, to verify the various objects that pass through the magnetometer sensor. For the scope of our project, first, the magnetometer sensor will detect the threshold level depth field whenever a various object such as car pass through the sensor as our input signal. Second, the Arduino Uno will act as the microcontroller to receive the data from the magnetometer sensor in the transmitter node. Third is that the RF433 MHz transceiver module will allow the information to and from the transmitter to the gateway at the receiver node. Fourth is that the Wi-Fi module ESP8266 will have connected to the receiver and allow the information to be transmitted to the cloud. And lastly, the user is able to monitor the number of vehicles from the record in the cloud through IoT platforms such as Thingspeak. Methodology. A vehicle approaching the magnetometer, the partial destruction of magnetic field happens. Total destruction of magnetic fields where vehicle detected and counted. Recovery of magnetic field after vehicle passed by.
I will continue to present the transmitter node. This is transmitter node, which for hardware part, it mainly consists of magnetometer sensor HMC5883L, Arduino Uno R3, and RF433 MHz transmitter, while for software part, we are using Arduino software. This is receiver node, which it is divided to two parts, for hardware and also for software part. For hardware, it mainly consists of Arduino Uno R3, RF433 MHz receiver, and Wi-Fi module ESP8266, while for software we are using Arduino software and also Thingspeak. Block diagram. This is the block diagram for transmitter node. When the vehicle are passed by, there is a change in Earth magnetic field that will be sensed by magnetometer. The Arduino Uno is a microcontroller board based on 80MHz 328P. It was encoded to collect information from magnetometer regarding the number of magnetometer sensor, radius of magnetic field at y-z field, and the number of vehicles passed by. It was also encoded to allow signal at frequency of 433 MHz to be transmitted. The data provided by Arduino Uno is then transmitted through the antenna inside the wireless transmitter module RF433 MHz. This is block diagram for receiver node. The data is received through the antenna in wireless receiver module RF433 MHz by demodulating the RF signal to recover the information. The Arduino Uno was encoded to allow signal at frequency of 433 MHz to be received. User can choose which magnetometer number and signal frequency channel data to be received in order to obtain the readings of magnetic field Z field and the number of vehicles passed by. Next, the information collected is transmitted into the cloud, computing through ESP8266. The ESP8266 will send the information to a server created and stored in the cloud. The information now can be shared and displayed in real time by accessing the IoT platform by using electronic devices like computer and smartphone. It will display on Thingspeak dashboard.
I will continue the presentation with our flowchart. Wireless magnetometer for vehicle counter flowchart. First, the magnetometer will detect the number of vehicles. Then, the data will be processed by a microcontroller, and the data will transmit through wireless transmitter module. The data will receive through wireless receiver module, and the data will be processed by microcontroller. And it will start to count the number of vehicles. If it is a success, the data will transfer over network through Wi-Fi module, and the Wi-Fi module will continue to monitor the data. And if it fails to count the number of vehicles, the loop will begin again on magnetometer detect the number of vehicles. Next, our flowchart for project design. First, we together research the data, and then we select the suitable sensor and components. We construct the wireless magnetometer transmitter and receiver circuit, and we write coding for both set of Arduino, which is a receiver and transmitter. We check if the coding works or not. If it works, we will build transmitter and receiver circuit on breadboard. If no, we write coding again for both set of Arduino. Next, we check if circuit works on a breadboard. If no, we build again a transmitter and receiver circuit. If yes, we develop monitoring system. And then we check if the monitoring system is function or not. If no, we develop again the monitoring system. If it functions successfully, we continue on modification and improvement of prototype. Next, our circuit design. As we can see, this is our circuit design for transmitter node and receiver node. For transmitter node, we have Arduino Uno, 433 MHz RF transmitter, and we use a magnetometer sensor. For the receiver node, we use RX 433 MHz, Arduino Uno, and Wi-Fi module ESP8266, which is not MCU. Next, IoT platform. We list the differences between these three IoT platform, which is UbiDots, Power BI, and Thingspeak. From the perspective of a supported device, for UbiDots, it is Adafruit, Arduino, Raspberry Pi, and Onions. For Power BI, the supported device is Adafruit, Arduino, and ESP. For Thingspeak, Arduino, Raspberry Pi, Particle, and ESP. For the data analysis and data visualization and dashboard, for these three IoT platform, it support the data analysis and data visualization. For also same on cloud service type, which is for UbiDots, Power BI, and Thingspeak. It use public or private. And for API, UbiDots, every request required token. For Power BI, use the generated API key. For Thingspeak, use API key.
Now, I will continue to explain about the result and discussion of our IDP2 project. This is the picture of functional prototype of our wireless magnetometer for vehicle counting. Picture on the right show the receiver circuit, while picture on the left show the transmitter circuit. This is the data obtained from the functionality testing that was done. The functionality testing was done to verify that our magnetometer circuit can detect any car that passes through it in real life. The testing was done in 4 different conditions, which is when the car is absent, when the car drives across the sensor, when the car is on top of the sensor, and lastly, when the car drove away from the sensor. This is the number of vehicles counted by the magnetometer sensor, and this is the data of reading of magnetic field at z-axis. The IoT platform that was chosen in our IDP2 project is Thingspeak. This is the Thingspeak visualization for real-time monitoring of 5 vehicle counting. The picture shows the dashboard of real-time data streaming at Thingspeak. This is the number of vehicle counted, which is 5, and this is the magnetic field, the number of magnetic field at x-axis, y-axis, and z-axis. The red graph is the same data as the number, but it shown in a graphical form. Next is signal strength in serial monitor. The signal strength is tested by adjusting the distance between the transmitter and receiver module from 1 meter to 5 meter with increment of 1 meter. As shown in the data, the signal strength is excellent because the average real-time delay is 1.28 or 1.29 seconds for all 1 meter to 5 meter distance between transmitter and receiver module. For the pattern of the magnetic field when the car drove across the sensor for 6 times. Magnetic field is distorted when it sends any ferrous object and the number of vehicles will increment by 1. The purple line in the picture represent the vehicle counted, and the blue, red and green line indicate the magnetic field at x-axis, y-axis and z-axis. When there is a distortion in the magnetic field, the magnetometer will start counting the number of vehicles as shown in the purple line. The process will continue if there is any ferrous object that passes through magnetometer sensor. For the accuracy of data, the number of vehicles that pass through the magnetometer sensor tested is 50, but not all of them was detected by the magnetometer sensor. When the distance between the transmitter and receiver is increasing, the number of vehicles detected will decrease, which cause the percentage of counting accuracy drop from 96% to 84%. Even though there is some drop in the percentage of counting accuracy, it still maintained above 80% for range of 5 meter distance as shown in the graph. Last but not least is the conclusion and recommendation. As a conclusion, we successfully display and monitor the number of vehicles in real time through Thingspeak. Next, the number of vehicles is counted with the change of Earth's magnetic field at z-axis through the fixed threshold value at 8T. The product weight can be reduced so that it is easier to be carried around. Next, the product can be improved by designing it with characteristics of low power consumption so that it can enhance functionality and longer battery lifetime and battery usage. That's all from me. Thank you.
Now, let me introduce to you our prototypes.
This is our transmitter node. The transmitter node consists of 3 components. First, Arduino Uno as a control unit of this transmitter system. Second, RF43 MHz transmitter is used to transmit the data to receiver. Third, HERTZ-5883L magnetometer sensor is used to measure the magnetization of the ferromagnet and specify the direction of the magnetic field at that point. This is our receiver node. Our receiver node consists of 3 components. First, Arduino Uno as a control unit of this receiver system. Second, RF43 MHz receiver is used to receive the data from the transmitter. Third, ESP8266 Wi-Fi module is used to establish a TCP connection mode with the clock of the Thingspeak.
After all, let's look at our real-time field test.
This serial monitor shows the received data from the transmitter node. It shows the XYZ magnetic field sensed by the magnetometer sensor in the transmitter node. The number of vehicle count is 0 as the car is absent from the sensor. The ESP8266 will upload the data to the cloud of Thingspeak. In Thingspeak, as we can see as our dashboard, the number of vehicle count is 0 where the data is updated in a few seconds ago. Magnetic field XYZ has updated to 8 letters data. As the Z-axis is 65, it is below than the threshold value that we have set. So, vehicle counter wouldn't count. This is the latest data that we have obtained.
Now, let's start with the first car passes the sensor.
When there is no ferrous object passes the sensor, the number of vehicle count will be 0. When there is a ferrous materials passes the sensor, which like car, the number of the z-axis will exceed the threshold limit that we set just now, and the vehicle will be counted as 1. When the car stays on top of the sensor, the value of the z-axis will exceed the threshold limit, which indicates there is metal present on the sensor. However, the counting will remain as the previous value. Once the car passes away from the sensor, the value of the z-axis will drop below its threshold, where the number of the vehicle count will still remain as the previous number.
Next, let's look forward for the car testing number 2.
That's all from me. Thank you.